This episode of Real Engineering is brought to you by Brilliant, the problem-solving website that teaches you to think like an engineer. Since its inception in 1958, NASA has been involved in countless strange and bizarre experiments in the name of advancing the United States' understanding of aeronautics. After all, NASA stands for the National Aeronautics and Space Association. Their mission is to pioneer the future in space exploration, scientific discovery, and aeronautic research. To do this, they have built and tested some of the weirdest planes the world has ever seen, each designed to push the limits of our understanding and evaluate the value of new, innovative designs. The X-5 featured variable sweep wings that allowed the plane to alter its sweep angle during flight. The X-15, a sleek, rocket-powered plane designed to push for the record of the fastest plane in existence, smashing into the hypersonic regime at Mach 6.7. And the X-29, with its odd forward-swept wings, gave us valuable data on the flight characteristics of this interesting wing configuration. These are all weird and wonderful planes, but one stands out to me as the weirdest. A plane that looks like the weird love child of the X-5 and the X-29. A variable sweep wing, but with a single wing pivoting about a single point, resulting in the plane having this bizarre asymmetric wing configuration with one wing pointing forward and one pointing backwards. What could the designers of this bizarre plane have been thinking? What advantages did they possibly foresee? The primary advantage of variable sweep wings was well established before the AD-1 with the X-5 experimental aircraft, which first flew in 1951 when NASA was called NACA, when the organization was focused purely on aeronautics. Variable sweep wings have a couple of advantages. During takeoff and landing, you want to maximize lift so the plane can minimize its speed, making it easier and safer to take off and land, particularly on short runways like aircraft carriers. So, a variable sweep wing can take off with its wings set to its lowest sweep angle, maximizing lift. Then, as it speeds up and generates more lift, it can increase its sweep angle, which lowers the drag the wing generates as a result of the lower frontal area. Increased sweep angle also increases the critical Mach number of the plane. The critical Mach number is the speed at which supersonic flow first appears at some point along the plane's surface. This happens before the plane itself reaches supersonic speeds because air speeds up as it travels across the wing's upper surface. This can cause some funky aerodynamics as flow separates from the wing's surface when supersonic speeds are reached, which can interfere with control surfaces and drastically increases drag. This prevents some planes from flying faster. For example, airliners cruise just below critical Mach number, so increasing the critical Mach number is advantageous. To understand this, let's look at the flow components over the Bell X-5's wing at its lowest sweep angle, 20 degrees. Here, we can separate the airflow into two components: spanwise flow, which flows along the wing, and chordwise flow, which flows along the chord of the wing. The spanwise flow runs along the length of the wing and does not accelerate and thus does not lower the critical Mach number. At lower speeds, when supersonic airflow is not a worry, you want as much of that airflow to be chordwise, which is the flow that generates lift. However, as the speed of the plane begins to rise, we are generating more than enough lift thanks to the increased airspeed, and thus can afford to convert some of that airflow into spanwise flow. We do this by increasing the sweep angle, which the Bell X-5 could do in flight to a maximum sweep angle of 60 degrees. As the sweep angle increases, a larger portion of that airflow is converted to spanwise flow, which increases the critical Mach number. However, it can cause some troublesome stall characteristics. Because a large volume of air is now originating at the root of the wing and traveling to the tip of the wing, stall will begin at the tip of the wing and move towards the root. This is a problem because our ailerons, the control surfaces that allow us to roll the plane, are located on the outer wing. If a stall occurs on the outer wing, we lose roll control. A major problem for, say, a fighter jet attempting a high angle of attack maneuver while maintaining full control. And this is one of the problems the forward swept wing was trying to fix, like the X-29s, which we have explored in a previous video. This reverses the direction of the spanwise flow, so it originates at the wing tips and travels to the root of the wing, meaning stall occurs at the root of the wing first, allowing us to maintain control of the plane for much longer. Not only that, but it reduces induced drag as a result of the wingtip vortices, where high pressure from the lower wing travels and mixes with the low pressure air on top of the wing at the wingtips. So the advantages of variable sweep and forward swept wings are established, but this plane is some weird, indecisive Frankenstein's monster blend of both. We have one wing forward swept and one wing backward. As you have probably guessed, this bizarre asymmetry results in some strange control issues. The side force on the plane, the force that attempts to push it to the side, increases with the sweep angle, as more of that spanwise flow is redirected down each wing in a single direction. To compensate for this, the plane has to increase its bank and side slip angle. Flight at the maximum sweep angle of 60 degrees at 260 km per hour required 1 degree of nose right side slip and 7 degrees of right side down bank to remain in straight and level flight. As we saw, the sweep direction impacts where the stall occurs. The forward-pointing wing will first stall at the root, while the rear-facing wing will first stall on the wingtip. On top of this, the rear-facing wing stalled earlier than the forward-facing wing, meaning we lose lift on one wing first, causing the plane to roll and yaw to the left, while also having decreased ability to control roll as we lose aileron control on that wing. If not recovered, this would result in a deep spinning dive. There are more stability and control issues with this plane that I can explain in this video, but I have linked an excellent NASA report in the references for the aviation nerds that want to really dive deep into this complicated subject. The weird aerodynamics were obviously predictable, so what were the anticipated advantages of this bizarre configuration? The first and most obvious is the simplification of the sweep mechanism. A single pivot point for a sweep mechanism is simpler in construction than a twin pivot, but it also drastically reduces the stress being placed on the mechanism. To understand this, let's first see how the forces on the mechanism changes as the sweep angle increases. Starting with the oblique wing. Let's imagine this as a simple beam that is being pushed upwards at its endpoint. At 0 degree sweep, the beam is simply under symmetric bending, which means the center pivot point is only being pulled upwards, creating tension in the linkage, attaching it to the plane. As the sweep increases in level flight, the forces should remain the same, meaning that linkage is only ever in tension in level flight. Now let's imagine a single wing as it rotates around this pivot point. Once again, we will imagine it as a beam being lifted upwards. Here, there is no equal lift on the other side of the pivot point. So, this manifests in the mechanism as bending, not tension. And as the sweep increases, we begin to incorporate a torque around the y-axis of the plane, as the force lifting this beam gets further from the center of mass. These more complicated forces result in a pivot that needs to be stronger, and we need two of them. So, a single pivot point reduces the complexity and structural weight needed to facilitate a variable sweep wing. Next, we reduce wave drag as a result of conforming more closely to the area rule. This simple rule tells us the distribution of the cross-sectional area along the length of a transonic or supersonic plane should look something like this. That includes the wings, engines, everything. This gradual increase and decrease of cross-sectional area results in a reduction in wave drag, which is the drag that arises from shock waves forming around the plane as it approaches the speed of sound. So let's take a cross-sectional scan of the early version of the F-102 Delta Dagger, which was designed with a straight fuselage. It looked like this. We can see sudden bumps where the engine nacelles protrude from the fuselage, and a steep rise in cross-sectional area as the large delta wing increases in width, before a sudden drop along the straight trailing edge of the wing. This plane would have had quite a lot of wave drag because it deviates from the ideal distribution so much. So, the engineers later redesigned the F-102 so the fuselage tapered in along the length of the wing, thus decreasing the rapid rise in cross-sectional area as the wing widened. This decreased fuel consumption and increased the plane's top speed. Now, you probably see where this is going. By having one wing pointing forward and one pointing backwards, it naturally distributes the cross-sectional area of the wing over the entire length of the plane, allowing it to conform more closely to the area rule and thus decreases the effects of wave drag. Finally, traditional variable sweep wings have one last disadvantage. As the sweep of the wing increases, the center of lift of the plane shifts backwards, which, if not compensated for with pitch controls, will cause the plane to nose down. Using the control surfaces in this way will increase drag to keep the plane in straight and level flight. By having one wing shift forward and one wing shift backward, the center of lift remains relatively static and pitch trim does not need to compensate, decreasing the fuel lost to drag. The designers of this plane envisioned it as a plane that could take off from short runways and be capable of loitering in the air for extended periods of time, making it suitable as an air-to-air refueling tanker or submarine hunter. In the end, any advantages the designers sought using this flight configuration did not overcome the extreme disadvantages it experienced in stability and control. It incorporated all the structural issues associated with forward-swept wings, which we have explored in a previous video. It required extreme trim alterations in straight and level flight, and became near impossible for a human to control while performing extreme maneuvers. Even its more traditional brother in symmetric variable wings fell out of favor in the 70s due to its own disadvantages in heavy mechanisms and trim drag, and advances in flight controls and materials made delta wings the new norm, but that's a video for another day. NASA knows the best way to learn is by applying new ideas themselves and measuring the results. Learning by doing is essential for education. That's why Brilliant continually tests your knowledge as they take you through complicated subjects like this classical mechanics course, which gives you all the tools to understand the physics of the world around you, and prepares you for more complicated courses like quantum mechanics and special relativity. Getting something wrong isn't punished. You get to see the correct answer and the explanation of how it was found, and you move on. Brilliant is the perfect place to hone your skills, with easy-to-follow, curated courses that will take you from knowing nothing to having a well-rounded understanding of the building blocks of an engineering career. Brilliant's thought-provoking math, science, and computer science courses help guide you to mastery by taking complex concepts and breaking them up into bite-sized, understandable chunks. You'll start by having fun with their interactive explorations, and over time, you'll be amazed by what you can accomplish. If you are naturally curious, want to build your problem-solving skills, want to develop confidence in your analytical abilities, or, like me, find fulfillment in continual lifelong learning, then get Brilliant Premium to learn something new every day. If you are looking for something else to watch right now, why not watch my previous video about liquid metal batteries, which may form the missing link in renewable energy grids, or Real Science's latest video detailing the astounding biology of the tree frog that allows it to freeze solid every winter and survive.